Hello, welcome to Zeta Explained, and today we're going to be talking about the Riemann von Mangoldt formula. And so what we're trying to do is to estimate the number of non-trivial zeros of the Riemann zeta function inside the critical strip. And in episode 19, we proved that this function n of t, which is a function that counts the number of zeros inside the critical strip up to t. So remember, the critical strip is this kind of infinitely long rectangle that has bounded on the left by 0 and on the right by 1. And if you start as the imaginary part 0 and count up to t, then n of t is the function that just tells you how many zeros there are inside this finite rectangle. And we showed in episode 19 that n of t is big O of t log t. But today we're going to obtain a much more powerful result. So with the big O, we've only seen that this is an upper bound. So in theory, the growth rate could have been slower than this. And also, we don't know anything about what the coefficients are. So today, what we're going to do is we're going to use the Adamar factorization of zeta from episode 20, and we're going to have more precise asymptotic on n of t. So this is in fact what we're going to get. That n of t is actually equal to t over 2 pi times log of t over 2 pi minus t over 2 pi, then plus big O of log of t. So this equation is like a lot more precise than this one. And in fact, it's extremely precise. So I'm actually going to kind of show you a demonstration real quick. Let me see if I can pull this up. Give me a second. Okay, so this is the LMFDB. It tells you kind of how many, it has a lot of like data sets of like math things. So today I'm going to be using it on the zeta function. So I pulled up the data set for the zeros of the zeta function. This tells you all the non-trivial zeros up to, what is this number, 100 billion. And right now it's set to only output the first 100 zeros. So you can see a list of the zeros, the first 100 zeros of the zeta function. It's kind of starting at 0 and going up. And remember, we're only looking at the non-trivial zeros. And this thing notes that they all have real part 1/2, at least the ones found so far. So they all satisfy the Riemann hypothesis. So they're just telling you what the imaginary part is. So the real part is 1/2 for every single one of these things. And you can see the growth rate of this thing. It starts at like 14. This is the first zero is at 14. The second one's at 21. The third one's at 25. Let's say I pick 1,000 of them. So we got like 14, 21, 25. So it's kind of going up by 7, going up by 4, going up by 5, going up by 2, going up by 5 again, going up by 3. So it's going up by like at least 1 every time. But if I start scrolling down near 1,000, you'll see that it's slowed down significantly. So in these last ones, it's like 14, like 1410, 1411, 1411, 1413, 1415. So it's going up by like 1, 0, 1, or 2 every time. And so the growth rate is significantly slowed down. So I'm actually going to tell it to tell me the first 10,150 zeros. And you'll see why I chose this number in a sec. Okay, so if you tell it to get a large enough list, it's just going to give you a kind of like a text file basically. And you can like go all the way down and see that there are all these zeros. And what I've done is I've copied this all to a Google Sheet. Okay, so here is the Google Sheet. And what I've done is I've literally just copy pasted this table over to a Google Sheet. So I have the number n, that's just an integer count. And then this column is the imaginary coordinate of the nth zero. And remember, the real coordinate is always 1/2 of the ones found so far, which all satisfy the Riemann hypothesis. And this is actually, I just plotted a graph of n on the bottom versus the imaginary coordinate of the nth zero on the top. And you can see it's looks kind of linear here, but like you can see the slope was higher at the start and slowed down. And if I go all the way to the bottom, I've kind of already highlighted a couple of numbers here. What you can see is that the 10,142nd zero of the zeta function has an imaginary part of 9998.85. And then the next one is the 1,000, or the 10,000, sorry, 143rd zero has an imaginary part of just over 10,000. So according to the Riemann von Mangoldt formula, I should be able to plug in 10,000 and it should spit out a number close to 10,142. So indeed, so what I've done here is I've taken just the number 10,000, typed into a cell, and let me see if I can make this part smaller or something. Sorry about that. And this is going to be using the von Mangoldt formula. So this formula, as you can see, is just saying this number divided by 2 pi times the log of that number divided by 2 pi minus that number divided by 2 pi, and then I'm going to add this mysterious 7/8 term, but I'll explain that later. So it's the same formula. Let me click back to the slides. So it's the same formula as this. So it's t over 2 pi log of t over 2 pi minus t over 2 pi then plus O log of t. As it turns out, you'll see later when we derive the formula that there's going to be a 7/8 term that I've kind of left out here, but that term will be there. So I've added the 7/8 term. And it indeed says that the number of zeros below the height 10,000, it estimates that there should be 10,142 zeros. Well, 10,142.96. So if we go back to this location, indeed there are 10,142 zeros below that number. And if you want to get really fancy, you can see that this number, it's like barely above like 10,000. So like if you set this number, so there's almost 10,143 zeros below this number, below 10,000. So you can see this is actually closer to 10,143. And just to convince you it's not just like a random thing that happens to work for 10,000, let's plug in like 5,000. And it says there should be 4,520 zeros of the Riemann Zeta function below the height of 5,000. So I'm going to try to find the 4,520th zero. 4520. Okay, so it's right here. So indeed, there are actually, so the 4,520th zero has a imaginary part of 4,999, and the 4,521st zero has an imaginary part of 5,000, over 5,000. So the number of zeros with a imaginary part of strictly below 5,000, or equal to 5,000, but equal or less than 5,000, is 4,520. So this formula is once again correct. Now, if you try to do this for other numbers, it's not always like perfectly correct. It might be like off by a few, like for some of these numbers. But you can see how accurate this formula really is. So there is like a pattern to these like zeros, even though they look kind of like random if you just kind of look at this. And so that's what we're going to be proving today. So in fact, if you keep going through that spreadsheet, like you'll see that the error will eventually start increasing because we have this error term of log t. So the higher up you go, the larger the error is. But if you'll note the error, if you look at the error relative to the actual number you're looking at, it's very, very, very small. Like log of t is very slow compared to like t log t. And one other fun note is that this formula, I think, is in our series so far, or in our video series, is the first proof that there are actually an infinite number of zeros in the critical strip. So remember, this formula is just kind of an upper bound, but we've kind of obtained a more precise bound. This is an upper and lower bound, essentially. So as t goes up, the number of zeros less than or equal to t, it just goes up like t. So we've kind of prove, if we can prove this, then we also prove that there are indeed an infinite number of zeros in the critical strip. And in episode 1, for this video series, I said you don't really need to know complex analysis. I'm going to be trying to teach you everything along the way. And that may or may not have been true for the last few episodes, but for this video, I think you'll basically definitely need to know complex analysis. So sorry about that. But I will try to explain some of the things, but this episode will require a lot of complex analysis. Okay, so I'm going to kind of state a sketch of the proof. So here's the theorem. Let n of t denote the number of zeros in the critical strip up to t. Then the Riemann von Mangoldt formula says n of t. I've kind of already explained this. I do want to note a little bit about the history of this, is that Riemann actually wrote down this equation in his 1859 paper about the Riemann Zeta functions. Remember, that's is a famous paper about prime numbers, and he analyzed these prime numbers using the zeta function. And nowadays, everyone calls it the Riemann Zeta function because of that paper. But he didn't actually prove this, and he said I think he said he got close to a proof, but wasn't able to kind of complete the proof. So it was proved by von Mangoldt in 1905, and now it's known as the Riemann von Mangoldt formula. And here's the rough proof sketch. So I'm following a book by Aleksandar Ivić. He takes the logarithmic derivative of the xi and zeta functions. And then he does a specific contour integral on this thing, the logarithmic derivative. So this is the xi prime of s over xi of s. This is Greek letter xi, and this is the Greek letter zeta. And then he uses the argument principle from complex analysis, and I'll explain a little bit more about this later as well, although I've already covered it in an earlier video, to count the number of zeros. So he actually gets that. So it's actually, this step is actually not too bad compared to the steps later on. So we'll find pretty quickly that the number of zeros, n of t, is t over 2 pi log t over 2 pi minus t over 2 pi plus 7/8, which is a term I've mentioned before, plus 1 over pi times this weird term, and then plus O of 1 over t. And then I haven't really defined what this contour integral is over yet, but I'll define it later. And you can see that even at this point, it already looks pretty close to the final equation. So like once you get to this step, I think you're already like, in terms of the formula looking like the correct number, it already looks like quite close. But there's still a lot of work to do with this part. So the next thing we'll prove is that the number of zeros in a finite strip of like height 1 is bounded by O of log of t. And then this is going to let us kind of show something about this integral, and we'll show that this integral is O of log of t. And if this integral is O of log of t, then you kind of replace this with O of log of t, and then log of t grows faster than this constant of 7/8, and it grows faster than this O of 1 over t. So you can kind of replace all this red part with O of log of t, and then that's how you get the Riemann Mangoldt formula. Okay, so let's begin the proof. And again, this is going to be a very technical proof, so be warned. So first I'm going to define a contour. I'm going to let D be the rectangle with these vertices. I'm going to pick -1 minus it, 2 minus it, 2 plus it, and -1 plus it. And then by the argument principle, which we covered in episode 13, so this is saying that if you have some analytic function and then you kind of draw some contour around where the contour itself doesn't hit any zeros, then you can say something about the contour integral of a logarithmic derivative of that function. So in particular, so this function is an entire function, so it is analytic and has no poles. So by the argument principle, when we do the contour in this kind of rectangle around xi prime of s over xi prime, that's going to count the number of zeros in this rectangle. And basically, the argument principle just basically says this is the number of zeros with multiplicity. It's also minus the number of poles, but in our case, there are no poles. And so in addition to that, I have an extra factor of 1/2 here, and that's because this contour is actually going to include both the positive and negative imaginary parts. So remember, each zero has kind of a complex conjugate zero on the other side of the real line. So since n of t is defined as only if you kind of start at like 0 and then go up, then n of t is going to be half of the number of zeros you find in this contour. So that's why there's an extra half. So you can write this as 1 over 4 pi. And then because there's an I here, we know that this integral is going to spit out a purely imaginary number. So I can also rewrite n of t as 1 over 4 pi times the imaginary part of this integral. Okay, so now we're going to try to figure out what this integral is. So here's the definition of the Riemann xi function. And some people use a 1/2 in front, but the book I'm following by Aleksandar Ivić does not do this. So we're going to define xi of s equals s times s minus 1 times pi to the minus s over 2, gamma of s over 2 times zeta of s. And I'm going to write eta of s as just this part, not to be confused with the Dirichlet eta function. This has nothing to do with that function. This is just a kind of term I'm using to kind of group this part together. And then we'll note that eta of s is equal to eta of 1 minus s due to Riemann's functional equation. So if you remember the episode 15, the functional equation basically says that if you just take this part in red, and then you kind of replace all the s's with 1 minus s, then it's like equal to this original thing. So because that's true, then eta being defined as that eta of s must equal eta of 1 minus s. And therefore, if you take the logarithmic derivative of kind of this thing, so you get eta of s equals s minus 1, s minus 1 eta of s, sorry, c of s equals that. Then take the log of both sides, you get log of c of s equals log of s plus log of s minus 1 plus log of eta. And then you take the derivative using the chain rule, you get this. And then using the residue theorem, you can compute the two integrals over here. So I'm going to, remember, we want to take the integral of this entire thing. But we can just split it into three integrals: the integral over this thing, the integral over this thing, and the integral over this thing. And the integral over these two things is pretty easy. These are kind of the most basic possible integrals. I'm sorry, I think I should have like a ds here, but I think you know what I mean. And so this is just 2 pi I, and this is just also 2 pi I. And this is just because the residue of both of these functions is 1, and I'm integrating over a contour that contains both of these points. And therefore, if I do an integral over d of both of these added together, that's just going to be 4 pi. So I'm taking the imaginary part. And once again, I should have a ds here if you want to be kind of technical about this. And here's kind of the next key idea here. So note that eta of s has actually two symmetries. So we first talked about this symmetry, and then there's also a conjugate symmetry. So I'll kind of explain both. So the eta function has a thing called the conjugate symmetry. So we explained this back in episode 15, I believe, where at least for the zeta function, it obeys this, and we can kind of assume that, we don't have to assume it, but I'm going to assert that this is true for eta as well as for zeta. And what this says is that if you take eta of any point, like let's say here, then eta of the point, if you reflect it across the real axis, is going to be the complex conjugate of the value at this point. And moreover, since we're like in this, I'm going to go back to this integral, so we're looking at the imaginary part. That means the value, if you only look at the imaginary part, then the value of eta here is just the value of the imaginary part of eta here is just negative the value of eta over here. And when you do an integral, so if you're going along the path in this direction, then you would think that if doing the integral like this way is like doing the integral this way, but it's actually not true because of the conjugate symmetry. It's actually going to be negative. So it's in fact the same as going this way. And because of this symmetry, eta of s equals eta of 1 minus s, then any point over here is actually going to be reflected over here. So the value of the point here is the same as the value of the point here. And moreover, if you think about the like 1 minus s for a bit and the neg minus s, then going in this direction, going up this line is the same as going down in this line. And then because of the conjugate symmetry, I can use it over here. So going down this line, it's going to reflect over here, and that's going to be going, so not going up the line, but going down this line. And what I've shown is something that's actually kind of might sound obvious, but you kind of have to prove it because this is just not true in general if you took a general contour. What we've shown is that the contour around one of these things, so let's say just this blue part, but if I divide it into 4 parts, if I take the integral over just this blue section, it's actually exactly 1/4 of the integral over the entire rectangle. And that's because I proved that the value of the value of like eta at each point here is kind of reflected 4 ways over here and in the correct direction. So there's no like negatives canceling each other out. So I'm going to kind of call this one L, the blue one. So we're going to kind of ignore the other 3 for the rest of the video. So we found that the imaginary part of the contour from 2 to 2 plus it, so it's from here to here, combined with the integral from 2 plus it to 1/2 plus it, so from here to here, so that's this whole blue segment, must be 1/4 of the total integral. So again, this is not true in general. If I just took an arbitrary function and kind of drew something like this, it would not be true that if I divided the contour into 4 even parts, that the integral over each of the 4 parts would be 1/4 of the total integral. But because of these two symmetries, it is true in this case. So the original contour I called D, so the whole rectangle was D, and I'm going to call this blue part L. So blue L is both of these segments in this order. Okay, so and then that's what I'm saying here. So the imaginary part of the integral of over D of eta prime of S over eta of S, which is what we were trying to figure out before, is equal to 4 times the imaginary part of the same thing, but over L instead of D. And then now we can do some math. So we're going to plug in the formula for eta now, and then we're going to do the logarithmic derivative. So take the log of both sides first, and then take the derivative of both sides. And then I do this imaginary part of the integral over L of this, and replace the eta prime of S over eta with this formula. Sorry. And that gives you these 3 terms. So just split up the integral into 3 integrals. And the first one, you're just integrating over a constant. And it turns out that if you take the imaginary part of it, if you think about the path that you're going up, remember the blue path kind of had 2 parts. It went like up this way and then went this way. And so the imaginary part of this is just going to be like this way. So you're going to take the negative 1/2 log pi and multiply it by the kind of distance you went up, which is t. So you get negative t over 2 log pi. And if you had you gone this way, the integral would be a real part, so it's not included here. And then in the next one, I am going to just kind of almost like use the fundamental theorem of calculus here. You have to be very careful with doing that with complex integrals. But the idea is that this, the way I got this was by taking the derivative of log of gamma of s over 2. So because this is now a line integral, it's not a like closed curve anymore. I'm just going to say that I can evaluate the antiderivative at this point and subtract the antiderivative at this point. And you have to be, again, you have to be kind of careful here because like you have to make sure like you can't, because of how complex log works, you don't go wind around the origin a bunch. But we'll see that everything does work out nicely here. So if you kind of put this back in the antiderivative, then if you plug in the parts that you're integrating over, so you start at the point 2, and then you go along here, and then you go to 1/2 plus it. If you plug in 2 to gamma of s over 2, s equals 2, then you get gamma of 1, so that's here. And gamma of 1 happens to equal 1, so log of gamma of 1 is equal to 0, so this part actually cancels out. And you're left with this term, so I'm taking 1/2 plus it and then dividing it by 2 over here. And then I haven't done anything with this zeta term because we're going to deal with this later. This is kind of the hardest part of the proof, actually. And we're going to use the Stirling approximation for the gamma function. So we discussed this in episode 19. The gamma of s is approximately the square root of 2 pi over s times s over e all to the s power, and then times this error term. And we're going to use the log version of it. So we're going to take the log of both sides, and you get this equation. And you kind of have to specify that the arg of s, so the kind of the angle of the complex number, the absolute value of that is less than or equal to pi minus delta, where delta is some number greater than 0, and you fix that number. And this is to avoid the usual branch cut of the complex log. So I'm not going to, basically the idea is that the log function is nicely behaved. Well, it has this singularity here, but if you were to start kind of like going along the log, there are kind of issues if you start like going around in circles, and you're not allowed to do that. So what we usually do is we kind of create a forbidden line, the negative real axis, and then to do something even stronger, because we don't want to go near the singularities of the gamma function, so I'm going to kind of pick some angle delta, and you're not even allowed to go like within delta of the real line in terms of angle. So you're allowed to go anywhere like up to that forbidden region. Okay, and we're going to use a version of Stirling's formula, so I'm not going to prove this second part. We are allowed to have a constant b, so it's basically exactly the same as this equation, except we have gamma of s plus b, and then there's just an extra b term here. So if you collect the log s terms, there's a log s here and a log s here, so the coefficients are s and minus a half. So this is just s plus b minus a half. And if you go back to our gamma function, so since what we're doing is we're thinking of t, like we're starting at kind of a point along the real axis and going up by t. So we're going to set b equal to 1/4, so the real part. So this is what we're trying to figure out. And then we're setting s equal to 1/2 it, this part. And then we're just applying this formula. Okay, so I'm going to plug in this formula in here. And because I'm taking the imaginary part, a lot of the terms I can actually kind of ignore. So for example, this part is a real number. This is just a constant, but it's real, so the imaginary part of it is 0. And then this part you have to be kind of careful with. So what I'm going to do is I'm going to take this log of 1/2 it and split it up. I kind of skipped the step here, but let me kind of see if I can draw it. So log of 1/2 it is equal to log. I'm going to split it up into a real part and imaginary part, equals 1/2 t plus log of I. And log of I is purely imaginary. So does that make sense? So this thing, log of 1/2 it is equal to log of 1/2 t plus log of I, just because of how log works. And then I can kind of like factor, like grab all the imaginary points out of this. So for example, this thing times this thing multiplied together is going to be imaginary. And then this thing times this thing is going to be imaginary. But the other two products are just real. So like negative a fourth times this thing is a real number, so I don't include it here because I'm only taking the imaginary parts. And also this thing times this thing is also a real number, so I'm not doing that. So I'm just taking these two things. So what I get is that I'm getting, so this is what, 1/2 t times log of 1/2 t, so that's this term. So this term times this term equals this term. And then this minus 1/4 log of I. So I haven't really figured out what log I is. I'm just asserting it's imaginary for now. But in case I don't know, I'm just going to say it's equal to imaginary part, negative imaginary part of 1/4 log I. I'll solve this in the next step. And then this part is minus 1/2 it, but the imaginary part of this is just negative 1/2 t, so that's over here. And then this error term is just, O of t to the minus 1, so I'm not doing anything with this for now. Okay, and finally I'm going to kind of solve this. So I'm going to move the minus t over 2 in front of this thing. And if you think about what's going on here, the log of I, what's the log of I? So I, let me see if I've run out of colors here. Let's say this is up the point I over here, and let's say the green is going along the unit circle. Then the log of that is, so the real part is going to be 0 because it's exactly on the unit circle. And the imaginary part of the log is going to be the angle to get here from the real axis. So you need to go pi over 2 to get from 0 to I. So log of I is going to be I times pi over 2. So which kind of, if you multiply it together, it gets I times pi over 8. But if you do the imaginary part, you can get rid of the I, so then you just get minus pi over 8. Okay, so you get this equation. And now I believe we're able to kind of combine everything together. So the next slide is going to have a lot of stuff on it. So kind of recap everything we did so far. So we first defined n of t as the number of zeros inside like a finite, like bounded region of the critical strip. And using the argument principle, we said that it's equal to this contour integral. D is the full rectangle, not just the like path L of c prime of s over c. And then we use the logarithmic derivative on the definition of xi to get this formula. And then we have to contend with eta, but since eta has conjugate symmetry and has this 1 minus s symmetry, then we were able to say that the integral over d is 4 times the integral over L. And then we found that the integral over L of eta of s, so just kind of continuing forth, is this formula. And again, this is just a constant, and this thing, sorry, this thing is just is a thing that we're not going to deal with yet. And then we said that this is equal to this term over here. On the last slide, we kind of like used the Stirling approximation and like computed everything out. And now what we're going to do is just kind of plug everything back in and just see if we can get something for n of t. So here it is. So apologies, so there's just a lot going on here because I'm just kind of plugging in every step from this part. So I start with 1 over 4 pi times this integral. I split out this integral using this equation, 1 over s minus 1 times eta prime of s over eta. And then I'm kind of do a couple steps at once. So both of these integrals are 2 pi I. So that's 4 pi I. But the imaginary part of 4 pi I is 4 pi. So I have this 4 pi over 4 pi here. And then now I'm going to do the integral of eta prime of s over eta of s. And I said that's 4 times the integral over L of this thing. And that thing is equal to this. So I plugged that all into this section. Or sorry, into this section here. So I'm saying this is just equal to this. So I literally just plugged that in. And the 4 comes from the 4 here. Okay, so if you believe me so far, because I haven't really done much math, I'm just kind of plugging stuff in here, then the next step is I can try to start simplifying this. So let's see, so what do we get here? So we get 4 and the 4 here cancel out, so this t over 2, this negative t over 2 log pi divided by pi is just t over 2 pi log pi. And then this thing, so we're going to not do anything with the zeta for now, but then I'm going to now substitute this thing here for this whole equation. And I think I might have, this parentheses should be over here, but actually, sorry, I think that's still correct. So, sorry, the parentheses is fine. So we're going to kind of move stuff out of here. So again, so this term now becomes what? So t over 2 n pi, so that becomes t over 2 pi, log of t over 2. And this t over 2 becomes then just becomes t over 2 pi because I'm dividing by pi here. And the negative pi over 8 becomes negative 1/8. And then this thing is still O of t to the minus 1 because dividing by pi doesn't do anything. And then this thing I just kind of multiply by 1 over pi to get this. And now I'm going to simplify these terms here. So let me kind of remove the drawings again. And what I'm going to note is that this thing distributes. So these two terms both start with t over 2 pi. And because of how logs work, I'm just adding log of pi to log of t, or sorry, negative log of pi, because there's a negative here, negative log of pi to log of t over 2. But when you subtract the log, you're basically dividing by that number. So this becomes t over 2 pi. So that's how I get t over 2 pi log of t over 2 pi. So this term. This term is just the kind of sum of these two terms using definition of log, or using just the property of log. And then I still have the t over 2 pi here, then the 1 all the way out here. So let's see, so there's still a 1 and then minus 1/8 become the 7/8. And then the O of t to the minus 1 stays the same, and this 1 over pi imaginary part of zeta remains the same. So the last formula we obtained is actually very, very close to what we wanted to do to prove the theorem. So the thing we want to prove, the final theorem in the end, is t over 2 pi log of t over 2 pi minus t over 2 pi plus O of log of t. And this is what we got so far from the last page. And it's actually quite close. We got the main leading term here, and we also got the second term as well. And we got the 7/8. So if you remember when I was trying to do a demonstration, I had this 7/8 in that formula because of this term. And then plus this error term, and then plus something with this contour of zeta. So all we have to do left to go from this to this is to kind of show that this part is O of log t. And I'm sorry, this should be a capital T here. Because as soon as this is O of log t, then the log O of log t grows faster than this term, and it grows faster than 7/8. So then we just have what we wanted to prove. So the way this will work is, so to prove this thing, we're going to split the L into 2 line segments and analyze each separately. But this is going to be no easy task. And before continuing, I'm going to give you a primer on what I think you should know about the complex log. So for a complex number z, and it's kind of easier to think of z as in polar coordinate, so r times e to the I theta, then the log of z is equal to the log of the modulus of z, or the absolute value of z, plus I times the arg of z. And you can think of just taking the log of both sides in this representation. So the r is the modulus, and this e to the I theta tells it how much to turn by. So if you get the log of a product here is the sum of the two logs, that's why you have two log things here. And then the first thing is just log of the absolute value, which is r. And then you have I times the arg of z. Well, the log of e to the I theta is just I theta, so the I, that's where you get the I from, and then the theta is just the arg of z, which is the angle. So like the point here, the arg would be like the angle here for a given complex number. And then in particular, the imaginary part of the log of z, so the imaginary part of this thing is just arg of z. And remember, we said the derivative of log of f of z using the chain rule is f prime of z over f prime of, or over f of z. And conversely, you can think of it as an integral. So if you take the integral of f prime of z over f prime of z, it should be kind of the antiderivative of this thing evaluated at kind of the endpoints of L. But again, because of how complex log works, it's not so easy because like you might be like winding around a circle a bunch. So you can't just kind of evaluate once. You have to figure out how much it's winding around. So I'm going to say that this integral is the change in arg of f of z as z travels along L. So remember, the imaginary part of this integral, the integral itself is just the antiderivative. So the antiderivative of this is just log of f of z. But I just said the imaginary part of log is the argument, arg of z. So the imaginary part of this is arg of f of z. And we want to track how many times arg of f of z, so how many times f of z is winding around the origin. And so we're going to kind of start doing some complex analysis. So remember, the contour L is composed of 2 line segments. So you start from 2 to 2 plus it, and then you go from 2 plus it to 1/2 plus it. And I'm going to claim that the integral along the segment 2 to 2 plus it can be written as this. So this is kind of what we covered on the last page. The imaginary part of this is the arg of zeta of 2 plus it. And really what I mean here is that as I travel the entire line up from here, so here to here, I'm going to have to count how many times I'm traveling around the origin. And zeta of 2, since we're starting here, zeta of, sorry, I probably shouldn't use red here because of the zeros. If I start at zeta of 2, then the output is just a real number, so the arg is just 0. So that's why I'm saying it's just the arg of this point. But I'm actually going to claim that zeta of s, when you go along this line 2 plus it, actually does not wind around the origin at all, as s goes up the line segment. So what I'm going to claim is that the absolute value of zeta of 2 plus it minus 1 is just bounded by a finite number. So I'm going to kind of put this in it's a infinite series form. Remember, when the real part of s is greater than 1, so 2 counts as greater than 1, you can write it as this infinite sum. And because I have a minus 1 here, I'm going to subtract out the first term of the infinite series. The first term of the infinite series is always just 1, no matter what s is. So that's why it's a sum from 2 to infinity. And I'm going to rewrite this imaginary part as a thing on the top, so e to the minus it log n. And then we use the triangle inequality to move the absolute value in the sides, but now it's a less than or equal to. And then the absolute value of this thing on the top is just 1 because that's on the unit circle. So I just get the sum from n equals 2 to infinity of 1 over n squared. And that's just pi squared over 6 minus 1, because if I had the sum from 1 to infinity, that's pi squared over 6. And this is going to be around 0.644. So starting at the point 1 on the complex plane, then I cannot leave a circle of radius 0.644 away from that. So because of that, the real part of zeta of s is always going to be at least 0.35, and therefore the argument can never, it can never wind around the origin. So if this doesn't make sense, I'm actually going to kind of illustrate on the next slide with some graphics. So here's kind of what I'm saying. On the left is the input s, on the output, or on the right is the output zeta of s. And I'm saying if you start at this black point, where we're starting the contour integral 2, then zeta of 2 is about 1.644. That's pi squared over 6. But then you start traveling up this line, what zeta is going to do is start winding around. But what I've proved in the last slide is that this winding around always stays inside this gray circle or gray disk that I've drawn. Its center is 1 and its radius is 0.644. So this is kind of what I'm saying. So as s travels up this line, zeta of s stays in a region to the right of real part greater than 0.35, and therefore the absolute value of the arg of s is definitely less than pi over 2. So pi over 2, so in fact it looks like it's bounded even more strongly than pi over 2. It looks like it's bounded like this. So the angle, the arg of zeta of s can never leave like whatever angle this is. But because I don't even need to calculate the angle, I can just say, it can't ever cross the imaginary, you can't cross like this line, the imaginary axis. So therefore the angle is bounded by pi over 2. And that's enough for what we need. So I'm going to say, okay, so this is just restating what we said before. So as s goes up the line, real part equals 2, zeta of s stays in a region to the right of real of s greater than 0.35, and therefore the arg is completely bounded. And therefore this integral, the imaginary part of this thing, is just the arg of zeta of 2 plus it. And since it doesn't wind around, then this is just O of 1. So it does not depend on how high t is. Like I can make t as large as I want, but this integral is still like bounded between kind of negative pi over 2 and pi over 2. Cool. So, but remember, this L thing that we're trying to integrate over is actually 2 segments. It's this vertical part and the horizontal part. So what we've just shown is that the integral over this vertical section is O of 1, not depending on t. And remember, what we were trying to show is that the integral over both parts together is O of log of t. So what remains to show is that this part of the integral, this horizontal section, is O of log of t. So if we prove this thing, then we're done with the theorem. So we prove that if you go up this line, it's already O of 1. So we just need to show that this part is O of t, or O of log of t, I mean. And this part is going to be pretty hard. I think there's just, I'm not going to be able to provide like too much intuition for the rest of the proof. Proving this part is just purely, I think it's almost purely technical at this point. So feel free to skip this if you kind of only want to see the intuition. So I'll first prove a bound on the number of zeros in a small region, and then we'll go back to the integral. So recall the Hadamard factorization that we found in episode 20 that's saying this. Remember, we're using kind of a log version of it, so this infinite product is actually an infinite sum over the zeros. So b, remember, is some constant, and the rows here, so this is the Greek letter rho, are the non-trivial zeros of the zeta function. So note that we will not include the trivial zeros at the negative even integers here, and it's because we originally found this factorization of the xi function first and then added some terms for the zeta function. So these are really only going over the non-trivial zeros. And then we're going to fix kind of sigma to be some number between 1 and 2, inclusive of 2. And then I'm going to kind of assert something that I'm not going to prove here about the growth rate of this term. So this term is gamma prime over gamma. And I'm going to kind of assert that this thing is bounded by log of t, if I'm kind of inside some, like fix some kind of sigma here. Or if I kind of bound sigma between kind of like 2 vertical lines. Then what I'm going to claim is that zeta prime of s over zeta of s is O of log of t plus this term. And I think this is pretty easy to show if you assume this to be true. So this term is just O of log of t. This term is a constant, so it's smaller than O of log of t. This term is O of 1 over t, so that's also gone. And this term is also a constant. So all three of these terms grow slower than O of log of t. So therefore, it is true that this thing is equal to O of log of t plus this final term. And then now we're going to let s equal 2 plus it. Then, if you remember in episode 6, we actually showed a formula for zeta prime of s over zeta of s when the real part of s is greater than 1. And indeed, the real part of s is greater than 1. So we're going to start on 2 and then kind of go up and down the line again. And for illustration, zeta of s, zeta prime of s, or over zeta is equal to negative times the sum of this thing, which is the von Mangoldt function. I'm not going to redefine it here, but the main thing you need to know is that it's always 0 or positive, and when it is positive, it is less than or equal to the log of n. So maybe here I should have stated it's positive as well. And moreover, if you kind of just like multiply this out times n to the minus s, like the zeta function, and because s, the real part is 2, if you just multiply this out, then this term just has an absolute value of 1. So I can just use the triangle inequality here. The absolute value of this thing is going to be less than or equal to the absolute value of the sum. If you take out the negative sign, the sum of this, and then I can split this absolute value into two absolute values, and this one is just 1, so that goes away. And then the von Mangoldt function is O of log of n, so which is much slower than any polynomial, so this thing just converges. And notably, this converges regardless of what t is, so this is also O of 1. So what we've shown is that this thing is O of 1. So if this thing is O of t, and this thing is what we're trying to figure out, so this is O of t and this is O of 1, then this thing has got to be O of log of t as well. Sorry, I think I kept saying log of O of t, but this is O of log of t. So this is O of log of t, this is O of 1, then this has to be O of log of t. And kind of cancel out this thing for this to be O of 1. So that's what I'm saying down here, that this sum over the non-trivial zeros must be O of log of t, when s is 2 plus it. And then now I'm going to take the real part of both sides. And remember, for the integral, I actually want to take the imaginary part, but I'm using the real part to kind of prove like a kind of auxiliary result that we'll kind of then use on the imaginary part. So we're taking the real part first. So we're going to write the zeros row as a plus bi. And then what we do know so far is that a is a number between 0 and 1, because we kind of proved that all of these zeros, all the non-trivial zeros of the Riemann Zeta function are in the critical strip. And it's going to be strictly between 0 and 1, so it can't even hit 0 or 1. And we proved all of this before. Then the real part of this term, so let's start with this one, is the real part of 1 over a plus bi. And we kind of do a classic trick where I kind of multiply the numerator and the denominator by a minus bi. So a minus bi over a squared plus b squared. So I've kind of eliminated the imaginary terms out of the denominator. Right, so a plus bi times a minus bi is a squared plus b squared. And if you look at this number, this is pretty easy to take the real part of. If you split the sum up, then a over this thing is going to be the real part, and negative bi over that thing is going to be the imaginary part. So the real part of this is just a over a squared plus b squared. And therefore, the sum over row of this real of 1 over row is just the sum over row of this thing. But remember, the zeros are distributed roughly linearly. It's a little bit more packed than linear, but it's like less packed than any like power greater than 1. But because this denominator has a b squared on it, this thing is just going to converge. So namely, this thing converges to a number and it does not depend on s or capital T. So capital T here is just the imaginary part of s. So this sum converges to a number not depending on s or t. So therefore, I'm going to call this part O of 1. And finally, I'm going to kind of look at the real part of this thing as well. So next step is this. So the real part of 1 over s minus rho, I'm going to do the same thing here, but the formula is a bit more complicated. I take 2 plus it, that's s, minus rho is a plus bi. And I kind of skipped sorry, actually I don't skip a step right here. So I'm just rearranging the terms in the denominator to put the real terms together and the imaginary terms together. So the real terms here are 2 and negative a, that's here, and the imaginary terms are it and minus bi, so that's I times t minus b. And then for this step, I kind of skipped a step here. I'm just going straight from this to this. So the real part is just the whatever the real part is here, this a, so it's 2 minus a, so the 2 minus a goes here. And then the denominator here is the square of these two things. So it's 2 minus a squared and then t minus b squared. And then I'm going to claim that this thing is greater than 1 over 4 plus t minus b squared. And this is because of what I know about a here. So remember, a is a non-trivial zero of the zeta function. So a, the real part of a is going to be between 0 and 1. So 2 minus a must be between 1 and 2, which is more than 1. And then 2 minus a squared is definitely less than 4. It's between 1 and 4, but I'm just going to say it's greater than 1 over 4 plus this thing. And therefore, this thing is O of log of t, because this thing is the sum here. But I'm saying if this thing is O of 1 and this thing is O of log t, then this part has to be O of log t. So that's kind of what I'm saying down here. Okay, so this thing is O of log t. And then now consider I'm going to say we're going to consider only the zeros where where b, the kind of imaginary part of the zero, is between t and t plus 1. And I'm going to try to consider what this thing is, so the number of zeros in a region of the critical strip. So like if you imagine this is a critical strip, I'm kind of analyzing how many zeros can there be in like kind of a horizontal rectangle of like height 1. And that's like this number. So n of t is the number of zeros up to this point, and then n of t plus 1 is the number of zeros up to the higher point. So the subtraction of the two, difference of the two, is going to be the number of zeros in between those two. And I'm going to claim for these zeros, the number of those zeros is this number. Then this thing is going to be at least 1/5. And the reason is that for these zeros, the t minus b, or the absolute value of t minus b, is between 0 and 1. So if you take a number between whose absolute value is between 0 and 1 and square it, then it's going to be a number between 0 and 1. And therefore 1 over, like a number that's between 1/4 and 1/5 is going to be greater than or equal to 1/5. So therefore I may split the zeros from before. So what I'm trying to do is I'm trying to add up all of these zeros, right? And I know these are all like real numbers here, like t and b are both real numbers. And I'm saying I proved that this whole sum is O of log of t. And what I'm going to do now is I'm going to split this sum into two sums. One is summing only the zeros where the imaginary part is between t and t plus 1. And the second sum is the infinite sum of all those other zeros. And I'm kind of going to use the fact that both of these are sums of only positive real numbers. And what I'm going to get is that this thing, since the thing I'm summing over is at least 1/5, so this thing is at least 1/5, and the number of things I'm summing over is kind of by definition this thing. It's n of t plus 1 minus n of t. So again, this is a positive number, or 0, and this thing is also a positive number. And we know that the sum of these two numbers is O of log of t. So therefore it must be that each of these two individual things is also O of log of t. Because like let's say that n of t plus 1 minus n of t was like higher than O of log of t. Well then, like since this thing is positive and this thing is positive, this second part cannot cancel anything out from the first part. So then that would kind of contradict that the sum is O of log of t. So therefore, this thing has to be O of log of t. But it's because it's a big O, I can just kind of get rid of this coefficient. So therefore, I can say that n of t plus 1 minus n of t is O of log of t. So therefore, I kind of have this interesting bound here, and we'll be using this a lot, that if you go up to some height t, then the number of zeros between in the critical strip between t and t plus 1 is kind of uniformly bounded by some constant times log of t. By uniform, I just mean it's the same constant regardless of how high you are up. Okay, so we're going to kind of use this now. So now we know that the number of zeros between t and t plus 1 is less than a constant times log of t. Okay, so we finally have the power now to kind of analyze this second part of the segment. So remember, the integral we're doing looks like this, and we determined that the vertical part is O of 1, and what we're trying to do is figure out that this horizontal part is O of log of t. So we're going to once again use the kind of Adamart factorization of zeta. It's this formula. Not going to re-explain it. And what we're going to do is we're going to plug in two values into this formula and then subtract. So we're going to plug in s equals sigma plus it, and then also s equals 2 plus it, or sorry, just plug in both of these values kind of into this formula. And if I subtract, I'm going to get this. So what's going to happen is the b is just a constant. That's going to cancel out when I subtract. This thing's a constant. That's going to cancel out. This thing is O of 1 over s, or 1 over t. So the subtraction of those is going to be definitely less than O of log of t. And then this thing is O of log of t. And then remember I said that zeta prime of s over zeta of s, so this is only one copy of it, but the second copy when I subtract is zeta prime of 2 plus it over zeta of 2 plus it. But I already showed that that this logarithmic derivative, if you have the real part 2, is just bounded, like it's less than a constant no matter what t is. So that's also a constant, and it's O of 1. So I can ignore that term. So the only remaining terms are these terms, and when I kind of have two copies of this equation out, then subtract the 1 over rho is also going to cancel out because the 1 over rho does not depend on what s is. So I'm going to get the sum over all rho of 1 over rho, and then subtract the sum over all rho of 1 over rho. So that's going to cancel out. So the only remaining interesting term then is this term over this sum over all the non-trivial zeros, and that's going to be rho sum over rho of 1 minus 1 over s minus rho. That's this thing. And then when I plug in 2 plus it, it's going to be, if you replace s with this thing, then it's going to be 1 over 2 plus it minus rho. And then what we're now going to do is we're going to split the non-trivial zeros of the zeta function into, let's suppose rho is equal to a plus bi. We're going to split them into two parts, and one part is such that b minus t is greater than or equal to 1, and then we're going to split into a second part where b minus t is less than 1. So we're going to start with the greater than or equal to 1. Then if you take the absolute value of this thing, and our idea is going to be show that both of those things are O of log of t, and then therefore we'll be able to get a result later. So 1 over s minus rho minus 1 over 2 plus it minus rho. So we're just going to kind of add the partial fraction. So we're going to just multiply this thing by the denominator here, and then multiply this whole thing by the denominator here. And I'm going to get this thing. And then the it and the rho's in the numerator cancel out. So I just get 2 minus sigma here. And then if you remember, what I'm summing over is, so sigma here does not refer to the real part of a 0, which is that's a, where a is between 0 and 1, but sigma here is like I'm doing this integral, and the bound here is 1/2 to 2. So sigma is a number between 1/2 and 2, so this is at most 1.5. And then also, if you think about some geometry down here, each of these two terms is at least as big as t minus b. So that's why, because they're on the denominator, I'm going to take less than or equal to as well. And the basic idea is I've already guaranteed that the height difference is at least 1 here. So if there's some kind of triangle where like S is over here, and then your kind of like non-trivial zero is here, and they have some distance between the two. So that's like this distance, like S minus rho, so S and rho. But because T and B are just the imaginary parts of them, so that's just like, so if I'm not sure where the x is, let's say the x is over here, then T and B are just these two numbers. So the height, if you think about a triangle, let's just do this actually. So this would be, the length of this part of the triangle would be T minus B. So that's why this is less than or equal to this. Okay, so this is the thing I had from before. Sorry, there's an extra kind of parentheses here. And using this bound, I'm going to consider this entire sum. And then this part's going to be a little bit tricky, so bear with me. So remember, we kind of split this sum. We wanted to split to find the sum over all rho, but it's kind of hard to do, so I'm going to split into two subtasks. The first task is to find the zeros where b minus t, the absolute value, is greater than or equal to 1. And then I'm going to consider only the case where b minus t is greater than or equal to 1, so without the absolute value. And then I'm going to claim the same result is going to apply where b minus t is less than or equal to negative 1. You can kind of do the same thing for that situation. Remember that n of t plus 1 minus n of t is big O of log of t. This is a thing we spent a while proving. Then the number of zeros in each region t plus k, b is between t plus k and t plus k plus 1. So that's saying, like, if I took, so let's say there's like a t here, and then here's like t plus 1, but then I'm going to keep going like t plus 2 and so forth. So I'm going to consider all the zeros in each region. There might be like zeros in like all of these regions. And I'm going to try to estimate how many zeros there are in each of these regions. But by using this formula, then the number of zeros in this region, t plus k to t plus k plus 1, is O of log of t plus k. And I'm also going to say that in this region, b minus t is at least k, because b is all the way up here, and t is down here. So b of minus t is at least k. So then this denominator term, this t minus b, or b minus t squared, is at most like 1 over k squared, because k is less than or equal to b minus t. And then finally, I'm going to note that, again, there's a lot of just like technicalities here that I don't really have much intuition for this, that log of t plus k you can write as O of something that's O of log of t plus k is O of log of t plus log of k. So I'm going to take this whole sum here and say it's less than or equal to the sum over the same sum of 1.5 over t minus b squared. So I haven't done any new stuff here. I'm just using this inequality. And then now I'm going to kind of switch the t minus b to a k, because this thing is less than or equal to k to the minus 2. So I'm allowed to do that because I have a big O here, so I just need this to be less than or equal to this. And then because the 1.5 is a constant, I can kind of get rid of it or change it to a 1. And then what I'm going to say is I'm going to re-index this thing. So instead of summing over rho, I'm going to sum from k equals 1 to infinity, and then count the number of zeros in each region, between where the zero is between t plus k and t plus k plus 1. And the number of such zeros is this thing, which we said is O of log t plus log k. So on the numerator, I have O of log of t plus log of k, then over k squared. And finally, I can distribute out the O of log of t, and I guess this should say O of log k. But this term just converges to a number that doesn't depend on t. And then this part also converges to a constant not depending on t. So then it's just O of log of t times a constant, then plus some constant. So that's just O of log of t. Okay, so remember, so this is back to the formula we were trying to look at before. After we kind of subtracted, we used the Hadamard factorization theorem, and then kind of subtract those two values. We got this term. And then this sum is too hard to deal with directly, so we kind of split it up into a section where b minus t is greater than or equal to 1. And we've seen that if you look at the section where b minus t is greater than or equal to 1, then this whole sum is O of log of t. So that's what I did here. I showed that this entire sum is O of log of t. And I can just kind of toss that O of log of t into this section because I already have an O of log of t. So then I can claim the remaining sum. So now only the things where b minus t is less than 1 is here, because I kind of split this sum into -1 and then +1, but the +1 is also O of log of t, so I kind of moved it into this O of log of t. And then we kind of want to kind of bound this as well. So in this case, we're actually going to kind of consider them separately. So we're going to kind of separate these out, and we're going to look at the green section here. So if you look at this term on the denominator, the absolute value of this thing is at least 1, because we know that a 0 of the Riemann Zeta function, or the non-trivial 0, has a real part between 0 and 1, so 0 is less than a less than 1. But then there's a 2 here as the real part, so the distance between this imaginary number and the 0 has to be at least 1, because their real part is at least 1 apart. And if this is at least 1, then the reciprocal is at most 1. Right, so and then because there are at most log t zeros in this section, because or the number of like n of t plus 1 minus n of t is O of log of t. But then like you technically have a height 2 rectangle here because this is absolute value less than 1. But that's also just log of t. That's just like 2 times log of t, which is O of log of t. So therefore I'm saying that this entire green sum looks like this. So it's like this whole thing is less than or equal to 1 in the absolute values. That's less than or equal to 1. But then the number of these zeros is O of log of t. So something that's O of log of t times 1 is just O of log of t. Okay, so even this sum, we've kind of took this green section and said the sum over that is O of log of t. So I'm going to kind of absorb that into the log of t as well. And then the only thing that remains is this blue section. And then that's this sum here. So I've shown that zeta prime of s over zeta of s equals O of log of t plus just this sum over the zeros that are within 1 of t, where the imaginary part is within 1 of t. And now we're really almost done. This has been going on for a while now, so we're going to go back to the complex analysis. So remember that the thing we are trying to find is the growth rate of this integral. So this might be so far back, like many, many minutes ago. And the last few slides, what we've shown is this result. So this is the kind of last equation from the last page. So what I'm going to do is I'm just going to do the integral. So the imaginary part of this integral, and remember the part of this integral I'm doing is, remember there was, a while back, there was this integral like this, and I showed that the integral along the vertical section is a constant, or it's at least bounded, so it's O of 1, and then we're trying to figure out this horizontal section of the integral, and that's this. And I'm going to replace this zeta prime of s over zeta of s with this part, so it's O of log of t, plus this sum over the close by non-trivial zeros. Okay, and then this integral is over a finite segment, so the length of this segment does not increase as t gets higher and higher. So I can just pull out the log t here, and this is a constant that's bounded, and therefore this whole part is O of log of t, and then just have to contend with the integral of this sum. And then I can actually interchange the sum and the integral because, well, for one, this is just a finite sum. This is not an infinite sum. For like a given t, there's at most log t times the constant zeros in here. And also the integral is also kind of over a bounded region, and nothing kind of blows up here. So therefore, what I'm left with is this sum over the non-trivial zeros of this integral. And if you do this integral, this is kind of what we talked about many slides ago, that the imaginary part of this integral is just the antiderivative. That's just log of s minus rho. But in particular, the imaginary part of log is just the arg. So it's just the arg of s minus rho. But if you think about the kind of graph we have here, it would look something like this. that if you have some s that you're looking at like on this line, and then some kind of nearby non-trivial zero, the zeta function, the arg difference of those two is actually going to be pretty small. But in any case, I'm just going to like you can just say it's like less than or equal to pi or something. Like you can say it's like definitely, or like this would be like 3/2 pi. Like you can say it's definitely the difference between the angles of these two things is like pretty small here. But I'm going to say it's definitely less than like pi or 3/2 pi, which means that this is just O of 1. And remember, the number of zeros here is O of log of t. So then this sum is O of log of t times O of 1, which is O of log of t. And then finally, this whole thing then is O of log of t plus O of log of t, which equals O of log of t. And therefore, we've kind of proven exactly what we wanted to prove. So we proved that this thing is O of log of t. So we're going to go all the way back to this thing that we found earlier. So remember, we first figured out a contour of the Riemann Zeta function and found this thing that almost kind of proves the theorem, but we had to contend with this part, which is very annoying and very difficult to work with. And then we actually found that this section is O of log of t, and therefore you just combine these together. So if you replace this with O of log of t, then you can cancel out this 1 over pi because that big O doesn't care about constants, and then this thing grows slower than O of log of t, and then so does this 7/8. So finally, we have proved the Riemann von Mangoldt equation. And again, this is a pretty long proof and very technical. So we've been kind of building up the last many episodes up to this theorem, so I'm kind of glad that we finally are able to do it. And I'm not sure if there will be that many more videos after this one because this is kind of the culmination of all these episodes. There might be one or two, but we'll see. Thanks for watching.